Bismillahirrahmanirrahim. Hello, dear students. I hope you are having a nice day. I welcome you all in class of Rudin analysis by Robert G. Bartle. My name is Azmat Ali, and we are discussing exercise 2.1. Lastly, we discussed first 16 question of the exercise. In today's short lecture, we will just discuss just three questions from question number 17 to question number 19. So let us start from question number 17. The question number 17 can be stated as prove the following form of theorem 2.1.9. What is the theorem theorem 2.1.9? This is the theorem 2.1.9. If A is a real number such that A lies between 0 and epsilon, where A is equal to 0, for every epsilon greater than 0, then show that A is equal to 0. But in question number 17, the difference from 2.1.9 is that here A is equal to epsilon also. While in the statement of theorem 2.1.9 we have 0 less than or equal to A less than epsilon. So the equality it's not equal sign is not included in theorem 2.1.9. So we have to show that for every real number, this inequality hold for every positive real number epsilon, then A equal to 0. So I will prove this question by using two methods. Method number one, this is an intuitive method. Given inequality, this is our given inequality, shows that it holds for all those values of A that lies in the interval 0 to epsilon. Because this is a closed interval, so clearly A will satisfy all those values that lies in this interval. As epsilon is a positive real number and can assume any positive real value, so if epsilon approaches to 0, that is if epsilon lies in the neighborhood of 0, then this inequality 1 holds only if when A is equal to 0. Let us elaborate the method number 1 by taking a numerical example. Suppose if I fix A is equal to 5, then this inequality becomes 0 less than or equal to 5, 5 less than or equal to epsilon. This inequality is true whenever your epsilon is greater than or equal to 5. But it is given that epsilon can assume any positive real value. Epsilon is positive and can assume any positive real value. So if your epsilon is less than 5, then this inequality will not hold. So it means suppose if my epsilon is equal to 1, then I have to shrink this inequality. So this inequality now hold when your A lies between 0 and 1. Now again, if I take suppose A is 0.5, then clearly this inequality hold for this choice of epsilon. But again, epsilon is any positive real number. So now if I take epsilon is equal to 0.05, then again this inequality will not hold. So as epsilon is any positive real number and can assume any positive real value, so if you take a smaller value of epsilon that approaches to 0, then this inequality 0 less than or equal to A less than or equal to epsilon can hold if and only if A is equal to 0. So this is the only possibility for satisfying this inequality. The method number 2 is a simple and very easy method. Suppose that on the contrary, we have to show that in the given inequality 0 less than or equal to A less than or equal to epsilon, this inequality hold for every positive real number epsilon. And in this inequality, our A is greater than or equal to 0. But we have to show that this inequality hold. If this inequality hold for every positive real number epsilon, then it must be that A is 0. As A greater than or equal to 0 shows there are the two cases, A is greater than 0 and A is equal to 0. We suppose on the contrary that a is not equal to 0, a is positive. If a is positive and we set an arbitrary value of epsilon, which is epsilon naught, which is equal to a. I mean to say, I am choosing epsilon naught. Epsilon naught is any arbitrary value of epsilon, and I am taking here this is equal to a, because I can take epsilon is equal to a because a and epsilon both are equal. So this implies 0 is less than epsilon naught and epsilon naught is less than or equal to a, because both they are equal. Therefore, it is false that a is less than or equal to epsilon naught for every epsilon. But it is given that this inequality holds for every positive real number epsilon, and in this inequality, shows that epsilon is always bigger than or equal to a. But now this shows that this inequality shows that epsilon naught, a particular value of epsilon naught, is less than or equal to a. So this is false. Hence, our assumption that a is greater than 0 is wrong. So we conclude that a is not greater than 0. It means there is only one possibility for a, that is a is equal to 0 here. In question number 16, this is also very interesting question, and actually this is related to question number 17. We have a and b, two real numbers, and we suppose that for every positive real number epsilon, this inequality hold, that is a less than or equal to b plus epsilon. We have to show that a less than or equal to b. On the contrary, we suppose that a is not less than or equal to b, a is greater than b. Here we have to show that a is less than or equal to b. We suppose on the contrary that a is greater than b. If a is greater than b, then a minus b is positive. So put a particular value of epsilon, which is epsilon naught, equal to a minus b over 2. That will be also positive. By adding b on both sides to make this form b plus epsilon, this becomes b plus epsilon naught is equal to b plus a minus b. What is the value of epsilon naught? This is a minus b over 2 here. So this, by taking LCM, we have a plus b over 2, and a plus b over 2 is less than a. How it is less than a? It is as we have assumed that a is greater than b. So by adding a on both sides, we have a plus a is greater than a plus b, or in other words, this is 2a is greater than a plus b. Dividing on a to both sides, we have a greater than a plus b over 2. That's why a plus b over 2 is less than a. This implies b plus epsilon naught is less than a, as epsilon naught is any arbitrary value of epsilon, and it is given that this inequality hold for every positive real number epsilon, for every value of epsilon. But we have the situation that b plus epsilon naught is less than a. So this contradicts with the fact that a is less than or equal to b plus epsilon, where for all epsilon greater than 0. Hence our assumption that a greater than b is wrong, and hence finally a is less than or equal to b. In question number 19 is a very easy question. We have to show that this whole square is less than or equal to sum of square divided by 2 for all a b belong to R. Show that the equality hold if and only if both are equal. Firstly, we show that if a and b are distinct, that is, they are when they are not equal, we show that this left hand side is less than this right hand side. So expanding the square, we have a square plus b square plus 2ab over 4 less than a square plus b square over 2. Cancelling out 2 from both sides, this gives a square plus b square plus 2ab less than 2a square plus 2b square multiplied 2 on both sides. Subtracting these three terms from the left side, we have 0 less than a square plus b square minus 2ab, and this can be enclosed in a minus b whole square, and this is the perfect square, and you know the perfect square for a distinct real number a and b always positive. So a minus b whole square is positive, which is true. So whenever this inequality is true, we have a truth that a minus b, a perfect square, is greater than 0. Now if a is equal to b, this implies a minus b is equal to 0, and if a minus b is equal to 0, then its square is equal to 0, or equivalently we can say that the a minus b square is equal to 0 means these two sides are equal, and by conversely we have if these two sides are equal, then a and b are equal. This shows that the equality hold when a and b are equal. Otherwise, you can just substitute the value of a and b in both sides. You can obtain the both same result from both sides. If you substitute a is equal to b here, this is equal to 2a over 2 whole square, and on the other side we have a square plus a square over 2. This is equal to a square and this is equal to a square. So in today lecture we have discussed first three questions from question number 17 to question number 19. I hope you have now clear understanding of today's discussion. So inshallah in the next lecture we will discuss from question number 20. See you in the next lecture. Take care. Allah Hafiz.